Hi and hello all. Let us talk about Wolff rearrangement. In Wolff rearrangement, in presence of a light, heat, or a reagent containing silver plus, an alpha-diazoketone rearranges to ketene. Ketene is very reactive and it can be reacted with water to get acid, or it can be trapped in some other way. So this rearrangement from alpha-diazoketone to ketene is known as Wolff rearrangement. Let us try to see the mechanism of this rearrangement. Let us first see how we can make this alpha-diazoketone. Consider an acid chloride. Consider its reaction with the diazomethane. So this is diazomethane. Let us write a resonance structure for this. This is another resonance structure for diazomethane. Let's show the reaction from this structure. As you know, CH2 minus is the negative center in this reaction, and this carbonyl carbon atom is the positive center. So CH2 minus attacks this carbonyl carbon atom. There is going to be a new bond between this carbon and this carbon. And as there is a new bond, an old bond has to break, and this pi bond will break, and both electrons in pi bond will move towards oxygen. So we get a structure like this. And look at this structure. This O minus can come back. The two electrons in this oxygen is going to be in between this oxygen and this carbon. That means there is going to be a new bond between this oxygen and this carbon. An old bond has to break. The Cl will break. The Cl will break as Cl minus. Let's copy down the whole thing and try to make sense of the curved arrows. The two electrons from oxygen is going to be in between oxygen and that carbon. So let me make that bond. That H was autocorrection and it was not needed there. Anyway, at the time of this bond formation, this bond will break. So now there are 5 bonds to this carbon, and it will not happen like that. At the same time, this bond forms, this Cl bond will break, carbon Cl bond will break, and actually the Cl minus will leave. One proton from this structure will get eliminated. Look at this CH2. This is very acidic. These hydrogens are very acidic. There are electron withdrawing group here and here on both sides. Let's show the breaking of hydrogen carbon bond in this fashion, and H plus will leave. That Cl minus and H plus together it is HCl. So HCl leaves from this moiety, and we have this species. We can write a resonance structure for this. This is another resonance structure for this one. We could write another resonance structure for this. Consider the electrons in this nitrogen is making a bond with this second nitrogen, making a triple bond here. And the two electrons in this pi bond shifts from there and make a double bond here in between this carbon and this carbon, carbonyl carbon, and this oxygen carbon bond breaks. So that can be visualized by curved arrows. So let's copy this thing and try to make sense of the curved arrows. This means a new bond here. Let me write that, and that extra hydrogen is autocorrection. That's not there. That's triple bond, and this double bond breaks at the same time, and this double bond is no longer there, and that's here. The pi bond is here, and at the same time this pi bond breaks, and that will be O minus. There's a positive charge on that nitrogen. So in presence of Ag plus, H nu or heat, this will undergo a rearrangement. It's easier to show this from this structure. Let us copy down the structure and show a mechanism there. The two electrons in this oxygen is going to make a new bond with this carbon. That can be shown like this. That means a new bond is forming to this carbon. An old bond has to break. The old bond breaking is this one, not the pi bond here. This bond, this carbon-carbon bond breaks, and that migrates to this, that carbon, that group migrates to this carbon. A new bond is forming to this carbon, an old bond has to break, and this will break, and that leaves a stable nitrogen molecule. So that's one of the driving force for this reaction. Let us copy the whole thing down and try to make sense of the curved arrows. So this arrow means there is going to be a new bond between this oxygen and this carbon. That's H is autocorrection. And now there are 5 bonds to this carbon. That won't happen. An old bond has to break. So this carbon breaks and this bond breaks, and these two electrons are going to make bond with this carbon. So there is going to be a new CH3 bond here, and at the same time this particular bond. This carbon-nitrogen bond breaks and the 2 electron goes to this nitrogen. That means the nitrogen got its electron and also carbon's electron. So nitrogen got an extra electron. So positively charged nitrogen will become neutral. So this species N2 that leaves. Or we can show this as minus N2 here, like this. Let's do a little bit of beautification here. Let's draw the carbon there. Let's show the carbon there. That looks better. This is nothing but ketene. So the Wolff rearrangement is this one. I have shown here the mechanism as a concerted mechanism. This bond is breaking and this migration is happening at the same time. This is the most agreeable mechanism, but still a mechanism with a carbene as an intermediate can be shown, and that is also a logical mechanism, but evidence kind of suggests that this is the mechanism, but it's not fully understood. So the ketene can be trapped in many ways. Addition of water is one way. Here the lone pair on this oxygen can attack this carbon, and we can show the bond is breaking and negative charge is forming on this carbon. So let's copy the whole thing down and try to make sense of the curved arrows. This means there is going to be a new bond between this carbon and this oxygen. Let's write that. This lone pair is the reason for that bond. Let's remove that curved arrow also. And so that H2, let's show it as two separate hydrogens. In this bond, we say one electron belongs to carbon and one electron belongs to oxygen. Actually, both electrons are from oxygen. That means this oxygen lost one of its electrons, so it will have a positive charge. At the same time, this bond breaks. This becomes a single bond, and that carbon becomes a negatively charged species. As both electron from this pi bond goes to this carbon, carbon is getting its own electron and this carbon's electron too. So carbon is getting an extra electron, so it will be negatively charged, and this carbon, negatively charged carbon, can pick up this hydrogen as H+, and this bond can break in this fashion. So this is nothing but a carboxylic acid. See, this is COOH. Let's clean up the structure a bit. So that's COOH. So this is carboxylic acid. So when a ketene reacts with water, we get a carboxylic acid. The rearrangement happens at this step with elimination of nitrogen. That's one of its driving force. And the product is ketene, and it can be trapped in different ways. One of the ways is to react it with water to form carboxylic acid. Like I said, this is a concerted mechanism. We can show a mechanism in which a carbene is formed and which on rearrangement goes to this ketene. That is also a logical mechanism, a reasonable mechanism, but the evidence favors this concerted mechanism more. Hope you understood the mechanism of Wolff rearrangement. Thank you.